Welcome back to our fifth coding video of writing a convolutional neural network model for image classification. In the previous videos, as we went through all of them together, we wrote the model class, we introduced the hyperparameters, device, model, optimizer, loss function, and I showed you how I mounted my Google Drive into my Google Colab. If you're using your local computer, you don't need to do this part. And we also did something that has nothing to do with machine learning. We were just like randomly selecting 8 images, looking at the images with their labeling, with their labels. And we also created perhaps one of the most important pieces of tools that we need for developing our model, and that is making a CSV that has the path to the images as well as their labels. So it is very important because our data set, the Pytorch data set that we make, directly gets information from this CSV file, to which we call metadata. And we also, in the previous video, we developed the MyFlower dataset. That's like the Pytorch dataset. That is sort of like a class of dataset that is wrapped around our dataset, and it had its own capabilities, such as getting the image as well as its label for any given index that it's receiving. We defined the necessary transformations we wanted to do. We made the data loaders, and then we divide the data loader into a train loader and a test loader. And basically, the rest was visualizing what happened to the images after transformation, and we particularly noticed 2 changes. One was all the images had the same size. That was because we did rescaling. And then the second was that all the coloring of the images was a little bit different than normal images, and that was mainly due to normalizing. So now in this video, we were gonna write the training loop. Now keep in mind, in terms of the body of the pieces that you need for development of a machine learning model, or in this case, deep learning computer vision model, we have written many of its items. For example, we wrote the model class, we wrote the dataset, we wrote the data loader, hyperparameter model, etc. The one thing that we need right now is the training loop. Everything else is already written down. So let's write down the training loop in this video together. Obviously, the training loop is a loop because it's an iterative process of learning and then relearning and then relearning on the same data set, which is the train set. So it starts with a for loop, and each iteration is called epoch, for epoch in range. And I did have a hyperparameter called num epochs. Now here, what we would like to do is to notice that within each epoch, we're still iterating through the dataset, because we cannot load the entire dataset at once. And that was the whole idea of using data loaders, because data loaders allow us to take mini batches of data, work with them, train, and again get another mini batch. So right now, that's what we need to do. We need to write another for loop, and then in this case, I will get index as well as x and y in enumerate of the train loader. And keep in mind, the index is not the index of images. Index is the index of the mini batch. So now that we have this, I always in the training loop, I always want you to bring that mentality into basically remember this mentality of systematically looking at the train loop. How many important pieces, how many necessary pieces is a training loop constitutes from, and that is 4 pieces. We had this in the previous video series, the MNIST dataset, and we have it here as well. And those four important pieces is basically number one, send the data to the device, prepare the data. If there's any extra transformation you need to do, you do it here. Next is the forward loop, propagation. And lastly is the backward propagation. So these are the four important pieces of a training loop. You definitely need these. You might need extra pieces as well, depending on how how you are customizing your training loop. But these four steps are definitely there. So let's just go through them one by one. Sending to device is perhaps the easiest thing that one person can do. X is X to device, and we have already defined the device, right? Y is Y dot to device. And keep in mind, the reason why X and Y have a dot to method is because X and Y are already Pytorch tensors. Now you understand why we need to transfer them into Pytorch tensors. That's because we need to be able to utilize their capabilities, one of which being the dot to method. So that's important for you to notice it. Obviously, we have done all kind of transformation on our dataset already. We don't need to do that anymore. And you can imagine, like, for example, different people have different perspectives on preparing the data. For example, if you don't like to, when you're defining your data set, if you don't like to make the label, basically transfer the label from a number into a one-hot vector, as I explained to you in the previous video, then this is the place to do it. But we have already done it in our dataset because I think and I recommend you to follow these footsteps to basically make sure your dataset class prepares the data in a way that it's absolutely ready for being fed into your model. Don't leave bits and pieces of this data preparation for like extra functions or like somewhere around here. The reason I keep it here preparing the data is that sometimes, and not in this case, but sometimes it's necessary to do some transformation, some stuff here. In those cases, we need to define this. But in this case, for example, we don't need it. So I just like leave it empty. But for forward loop, we have a y hat. And remember, y hat is just like the prediction that we make on the y, for the y. And that would be model x. So if my model receives x, it will return y hat, which is one estimation of the absolute, the correct values y. And now it's time to calculate the loss. And loss is basically the criterion, that's what we defined, criterion of a y hat and y. So now it receives y hat, it has the y, and then it can calculate the loss. And keep in mind, this loss that is being calculated is only pertains to this mini batch. Eventually, for each epoch, we need the loss that pertains to the entire data set. So what I need to do is to define a running loss, and I will set it to 0 at the beginning of each epoch. And then my running loss, every time there's a loss calculated, my running loss gets added with that mini batches loss. This way, I'm at the end of the day, I will calculate the running loss of basically the loss that represents the loss of the epoch. So at this point, our forward propagation is done because forward propagation ends by calculating the loss. Now, in the backward propagation, so I don't want to get into the foundation of deep learning and the concepts of it, but the idea of mini batch is that you train the model with a mini batch of the data, and then you basically do the back propagation for the same mini batch. You're still in one epoch. And then the next batch comes, you go forward, you get back. Go forward, you get back. And that's why the number of mini batch, the number of images in each mini batch can change the efficiency of your model, because these going forward and backward, the number of them directly relates and correlates with the number of mini batches. And that can affect your model. And you can see the one extreme of it is the stochastic gradient descent, where your mini batch is equal to 1. And the other extreme is that your mini batch is equal to the entire data set, which is, in most cases, we don't still have the infrastructure to basically feed the entire data set to the model, and it's not even efficient. So the most efficient way to do the training is to have the mini batches, and you got to play around with the number of mini batch. And that's why the mini batch number is actually a hyperparameter, because you've got to play around with its number, with the number, until you find a sweet spot where your basically your training is being done perfectly. So now in the backward, we always have some very similar 3 lines of code that you can literally copy paste. First is to set the optimizer on 0 grad, making sure that there is no gradient being carried over from previous calculations. And then you need to set the loss on the backward mode. And at the end, you say, Mr. Optimizer or Mrs. Optimizer, please go dot step. So we want 1 step going for the optimizer. At this point, we're done with our training loop. The only thing we want is to print some information at the end of each epoch. So I go 1 tab behind and say, let's print an F string. And in the F string, I would like to have epoch. Printing the epoch number. And then epoch loss. We can say the epoch number, the loss is equal to the running loss. So that's it. We can run this training right now and see what is being done. Okay, so if you recall, I had set the number of epochs in our hyperparameters to 4, so that's why our model stopped here. But a small thing I would like you to notice is that we started off from a very high loss, and then with every single epoch the value of the loss decreased. And keep in mind that the value of this loss is somehow reflects the differences between the prediction y hat and the value of the labels y. And so basically the difference between the prediction and the actual value is decreasing, and that's exactly what we want in the process of training to happen. One important thing was that it was basically very slow. I think it took the model 6 minutes to go through these 4 epochs. That's 1.5 minutes per epoch. It's not that of a big deal when it comes to training of the machine learning models, but keep in mind we're using a convolutional neural network that has only 2 convolutional layers. Sometimes when you talk about like a state of the art, you're talking about 100 layers of convolutional neural network. So having 2 convolutional neural network layer is really nothing with, and we also used very low number of filters, or like 3rd dimension for each CNN. So it literally it is literally a very light network, and it shouldn't take this time. And the main reason why it takes that much time is that the GPU that we have access to in our Google Colab is not a fancy GPU. It's still faster than running this network on a CPU. I can guarantee that, but it wasn't the fast training that I expected. So the two next things that are very important. Number one is to basically add the check accuracy function and basically evaluate the model, because the loss function the loss value that we are calculating here is being calculated on the trained data set. It's not a good technique, and in the next video I will explain to you why this loss value is not that really good. We need some accuracy level, and that accuracy should not be predicted on the training data set. It should be predicted on the evaluation or test data set that we have already made a data loader for. And the other thing that is important for us is basically, I think you noticed that during that 1 hour, 1 minute and a half, we expect to see something, see some progress. And we will also going to add some progress bar with some meaningful information taken out from every single mini batch in order for the user to be able to see something while the training is happening. Sometimes one epoch might take 1 hour, and it would be very beneficial if the user could get some information during that 1 hour, and that's exactly what we're going to do in the video number 7. So thank you for bearing with me in this video, and I will see you in the next video where we are going to add the check accuracy function, and we're going to retrain using the accuracy check. I'll see you there. Thanks.